Okay, so we talked about proportion. Now let's switch gears and talk about hypothesis testing with our mean. All right, so a math teacher claims that she's developed a review course that increases, keyword, the scores of students on the math portion of the college entrance exam. Based on data from the administrator of the exam, scores are normally distributed. Check it out. I've got a mean. That's a tip-off, right? The other ones I had a percentage, and that was my tip-off that I was talking about, a proportion. This one I have a mean, it tells me. Okay, so the teacher obtains a random sample of 1,800 students, puts them through the review class, and finds that the mean math score of the 1,800 students is 520 with a standard deviation of 115. All right, let's state our null and alternative hypothesis. Remember, every time we go back to that null hypothesis, it is the original data based on original data. All right. Therefore, my alternative hypothesis is also based on original data. Because this says increases, then I'm saying I'm going to increase my score that was currently set up at 514 from the administrator of the exam. Okay, now here's the real question. Test this hypothesis at the 0.10 level of significance. Is the math score of 520 statistically significantly higher? So we know it's higher, right? But is it higher? Is it worth it higher, right? Do you see what I'm saying? So statistically significant means, yeah, it's higher, but if it's a tiny little amount, is it really statistically significant enough to make an impact? That's what the question on hand is. Okay, so let's do this. We want to find our test statistic, so we're going to come back to our handy dandy formula sheet. Oops, wrong page. And our test statistic for the mean, and that's our t-score because I have a mean. So our test statistic for our mean here is going to be that formula. So let's use it. Again, if you're using StatCrunch in your homework and for your tests, then just use StatCrunch. Watch those videos in your notes for StatCrunch. I am doing this the formula way just so that you could see how this plays out. Okay, so let's pull our information. I know my formula here is x bar minus the mu naught and standard deviation divided by the square root of n. So we've got a lot of information we want to plug out here. So let's see what we've got. I know that my x bar here is 520 because that's my sample mean, right? My sample standard deviation is 115. My n, which I need n here, is going to be 1800. And my mu, which I didn't write down, is that 514. Okay, so let's plug in everything we know here. So T naught is equal to 520 minus 514 over 115 divided by 1800. Now again, you are on a video. Pause it. Check to see if we get the same thing. I get 2.213, which I'm going to round to 2.21. Now, when I'm talking about this t distribution, this t value, you always have to have those degrees of freedom. I'm going to scoot this up a little bit. I know that my n here is 1800. Well, my chart doesn't go to that. So when I'm looking at my degrees of freedom, this 1800 that I have, you're supposed to subtract 1, but because my chart doesn't go there, I'm just going to look at the 1000 row. All right, so here's what we're doing. We are going to look for the 2.21 in the 1000 row. So I'm going to come over here, and in my T chart, oh, I've got it all written up, don't we? I'm going to scroll down here to my 1000 row. And I am looking for the value 2.21. And there it is. 2.21 is going to be between these two values. And that's where I'm going to pull my p-value from. So let's see where we are here. Whenever I squeeze this back in, what columns am I looking at? If I take it all the way up here, I'm going at 0.02 and 0.01. All right? Okay, come back over here. I know that my degrees of freedom, those values from my chart, is 2.056 and 2.330. Those are the values from my chart. 2.056 was in the column of 0.02. 2.330 was in the column of 0.01. And I know that this 2.21 is between those. If you have a problem where you need an exact p-value, you have to use StatCrunch. If you have a problem where you're looking at the approximation, like in this situation, where my p-value goes between 0.1 and 0.2. So I'm just looking for that approximation. If I can find my approximation, then this works just fine. If you can't, if you need an actual p-value, then you have to use StatCrunch. All right. So remember, the same criteria holds. My p-value here has to be less than my level of significance in order to reject. So let's see what's happening. Let me go to black. My level of significance here is 0.10. So my question is my p-value less than 0.10? Well, look at what I have. If you have an exact one from StatCrunch, use it. If you have this approximation, the highest p-value I could possibly have would be 0.02. Yeah, that's less, right? So if my value is between these two and the highest it could possibly be is up to 0.02, that's definitely less. So yes, we reject that. Which means my level of significance here, my statistically significant, the data change, the score change is statistically significant. And there is sufficient evidence to support it. Therefore, there is sufficient evidence to conclude that we change our minds. And another way to say that is we reject the null hypothesis. Of 514 as a math score. And we see the review class helps. That review class raises the scores. So yes, we are looking at a statistically significant amount. So then it is valid. This review class is valid according to the data, right? Now in reality, we all know there's budgets and time and all the stuff that goes into this. But our job as statisticians is simply to look at the data, put down that data and see what the data tells us. The data is telling us that there is sufficient evidence to reject that. All right. Cool. All right. Get these submitted. Make sure you submit this week 13 problems and I'll take a look at it. If you have any questions, make sure you're emailing me. Otherwise, I'll see you guys next week.